Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is just to provide another example here of how to mathematically describe the motion of a particle moving along some sort of path, in this case defined by this quadratic. So we're going to be focusing on this particle. It's going to be moving kind of in the direction shown, basically right to left, at a constant speed of 75 feet per second. What we're going to try to do is calculate its velocity and acceleration vectors at a point where x equals 50 feet. So again, I'm going to use Cartesian coordinates to describe the path of this particle. So that means that we start by describing where it's at. So the vector that I've just drawn is the position vector that represents this particle. I'm going to write that position vector in Cartesian coordinates. So that's going to be xi plus yj. Now the velocity vector we can get by differentiating the position vector. So that's going to be x dot I plus y dot j. Now to save myself some writing here, I'm going to go ahead and calculate that derivative from this function. So y dot, when we look at this function, is going to equal minus 2ax x dot, because the derivative of x squared with respect to time is 2x dx dt, and the minus a is just a constant. And then when we differentiate the 15, we get 0. Okay, so we're looking for the velocity vector, and it kind of looks like we have it. However, when we glance it over, you'll notice that we don't have the x dot. We have the x, the a is a constant, but we don't have x dot. So the $1 question is, what do we do about that? So let's look at what we do have. You'll notice that our speed in this example is 75 feet per second. So to move on, we have to understand, how does the speed relate to this vector? Now this is the velocity vector, and the speed is the magnitude of that vector. So I can write out a Pythagorean theorem equation for this. That's going to be, and again I'm going to put NCU for note consistent units. So the magnitude is 75 feet per second squared is going to equal x dot squared plus the y component squared. So let's see, how about I write 4a squared x dot squared. If we go through and square everything. And I believe that we have everything we need here to solve for x dot. So in this example, the a is 0.0015 and the x is 50. So what I'm going to do here is I'm just going to pause this video here while we sort out the look for that numerical value here. All right, folks, we're back, and the solution of this equation for x dot actually yields two solutions, plus 74 and minus 74. Looking at our picture here, this object is moving to the left, so we kept minus 74 feet per second for x dot. All right, so now we know our velocity vector. Oh, whoops, I'm going to actually go back and do this, because I'm going to discuss the plus and minuses in context with this velocity vector. Let's just do this. Magnitude of x dot plus 74 feet per second. We'll talk plus and minus signs here when we, at this point right here, when we put in numbers. So our velocity vector, let's see, we're going to have x dot I. This thing I know is moving left, so at this point I'm going to put minus 74 feet per second I plus minus 2ax x dot. So that's going to give us minus 2. The a is 0.0015. X is positive 50. And then x dot, taking note that this object's moving left, so I'm going to use minus 74 feet per second. And again, this minus sign is because my observation, this guy's moving to the left. J. Oops, and if I leave the units out for one, I should leave them out for all. And again, let's do, yeah, a little bit sloppy math here. Let's do this. We'll get rid of that one. And we'll put the units outside, feet per second. So let me clean it up a little bit more. So we're going to have minus 74I. And you'll notice that minus and minus is plus, indicating a positive y dot. And as we look at this curve, as this object moves to the left along the curve, it is moving towards a higher and higher position. So the y dot should become positive. And when somebody gets a chance to run that for me, looking for a small positive value. Plus 11j feet per second. So there's the velocity vector at the instant shown. Now I'm going to go ahead and store this because I have a feeling we're going to need it. I'll take this and shrink that down and move that over to here because I have a feeling we're going to need it for the next part. Alright, so let's get rid of this. Next part is looking for the acceleration vector. And the acceleration vector is the derivative of the velocity vector. So we've got this equation here that describes the velocity vector. I'm going to go ahead and time differentiate it. We're going to get x double dot I. Well, I guess let's see, minus. How about we put minus 2a. Now we got to deal with this, the time derivative of that expression. So that has to be product rule. Derivative of the first times the second is going to give us an x dot squared plus the derivative of the second times the first. That's going to give us an x double dot times x. J. And again, the j and the I do not have time derivatives because they're not changing in direction. Now, as we kind of inspect this equation here, and I'm going to underline in red the things we do not know. Let's see, we don't know the acceleration, we don't know the magnitude of it. This is a constant speed problem, but that does not mean the magnitude of the acceleration is 0. What it means is the tangential component of the acceleration is 0. I suspect we're going to have to use that somewhere in this problem. X double dot, an unknown quantity, here and here. So x dot, and let me do in the green the things that are known. So these are just constants. X dot is a known value. We've got that somewhere previously. And x is a known value. So this equation has two unknowns, x double dot and the net acceleration vector. So we're going to need another equation to solve it for sure. The second equation we're going to get from this fact. It's a constant speed problem. Now the fact that the speed's constant does not mean the acceleration is 0. It means the tangential component of the acceleration is 0. Now what that means in the language of vectors. If I were to draw the velocity vector at the instant shown, I'll draw that in blue. That vector points something like this. If we draw the acceleration vector at the instant shown, and again, it's important to realize this is constant. So the acceleration vector does not have a component in the direction of the velocity. Therefore, it must make a, oops, let's do that in red. It must make a right angle to the velocity vector. So the next step is figure out, all right, how do we use this fact to write another equation? So what I'm going to do is I'm going to use the idea of a dot product to write another equation now. And before I do that, I just want to do a quick little review about a dot product and why what I'm going to do is going to work. All right, so let's say I've got a vector I'm going to call A, another vector I'm going to call B. So vector A, vector B. And here's some sort of angle between them. So when we calculate A dot B, Remember, that's equal to magnitude of A, magnitude of B, cosine of the angle between them. Now, if we kind of look at A cosine theta in context of this picture, A cosine theta gives what's sometimes called the projection of A onto B. If I draw it in this picture, it looks something like this. So the vector that I've just drawn in red is the A cosine B. If these vectors made a right angle, A would not have a component in the direction of B. So anytime two vectors make a right angle, their dot product has to be 0. That's the fact I'm going to use here to write another equation. What I'm going to do is I'm going to take the acceleration vector and dot it with the velocity vector. And that dot product has to give 0. And that's going to allow me to write another equation to solve this system, problem. So we're going to get rid of this. Go ahead and let's see what is that going to look like. So what I want to do here is I'm going to take the acceleration vector, dot it with the velocity vector, and I know this has to be 0 because of this right here. If the speed is constant, the acceleration cannot have a component in the direction of the velocity. Therefore, if you dot it with the velocity, you have to get 0 out of it. Now the velocity vector, I can dot it with this thing, which is perfectly fine. I've got nice, easy numerical values sitting right here, and I think I'll use these. And what I'm going to do is dot these in component form. So if I take A dot V, that's going to be this times this. So that's going to be minus 74x double dot. This is acceleration x component times velocity x component. Then we're going to take this times this. And I'm going to go ahead and write that guy first. Plus 11 times minus 2a times the quantity x dot squared plus x dot x, and then equals 0. I believe this equation hopefully only has one unknown. Let's see, x double dot. Yes, because x dot and x are known quantities. Right? So what I did is when I dotted these, I want to go through this. I just took the x component of this vector times the x component of this vector times y component of this vector times the y component of this vector. So that's a dot product in component form. All right, so let me go ahead and write this equation out here. 0 equals minus 74x double dot. All right, now we got to deal with this. Plus, actually, let's bring this out in front. Minus 11 times 2. Let's do that. 22a 0.0015. So I think this is all taken care of. Times x dot squared. 74 squared. The plus or minus does not matter here because it's being squared. Plus x double dot times x, which we know to be 50 feet. I'm going to take a moment now, pause this video because it's going to take a little time to sort that algebra out. There's no sense in adding time. Alright, so we're back, and I have my helpers go through and give me a value for this. So the solution of this equation here came out to be negative 2.4 foot per second squared. Now a little bit about interpreting our results. Here's the acceleration vector, which we know makes a right angle to the velocity. You'll notice this vector has an x component that points to the left, so we were expecting a negative number for that. Also, if you think about the geometry, it's kind of a shallow triangle. If I drew this a little bit more to scale, you'd see the y component should end up to be quite a bit larger than the x component just by looking at the geometry of this curvature. So I'm expecting a negative value for y double dot, probably larger than 2.4 foot per second squared. We can get the y double dot. Let's see. I guess that's this guy right here. So y double dot is going to be minus 2 times a 0.0015 times this expression. Let's see, x dot squared, and somewhere we had found x dot. right there, 74 foot per second. Now I wrote down this is the magnitude. It actually is moving left, which makes it negative, but it's squared away anyway, so I'm just going to put 74 squared. This part of the equation doesn't care if that thing's plus or minus. Plus x double dot minus 2.4 times x, positive 50. And would somebody please give me a value for that? Negative 16.1 foot per second squared. So our acceleration vector, 2.4 foot per second squared to the left, 16.1 foot per second squared down. And again, this is quite a bit larger because if I drew this a bit better, the viewer would notice that at this point right here, it's a pretty flat curve. So this acceleration vector makes a right angle. It's actually a bit more vertical than I have it drawn in the picture. Let me go ahead and write these results over to the right here. Minus 2.4i and minus 16.1j in units of feet per second per second. So I hope this video helps demonstrate how to describe the motion of a particle in a plane. Have a great day.